All right, good morning. Today I'm going to be competing in half of round 654. The reason I'm competing in half of it is, of course, because I'm so amazing that I only need 1 hour to solve the set. Not really. It's more because I thought I started at 10:30, started at 9:30 apparently. So I'm a little late. Yeah, ready to go, I guess. So yeah, we'll see. I'll just have fun. It's not rated for me, so it doesn't really matter. So I've got n sticks, one stick of each length from 1 to n. You can connect some sticks. If he connects 2 sticks that have lengths a and b, he gets 1 stick with length a plus b. 2 sticks that were used in the operation disappear. Okay, I see. He wants to create the maximum number of sticks that have the same length. It's not necessary to make all sticks have the same length. Yeah. So you can do n, and then you can make a bunch of size n. So 1, 2, I guess is it just n plus 1 over 2? So if you have 1, you can do 1. If you have 2, you can do 1. Yeah, n plus 1 over 2. So if you make all of them size n, then I think that's your best bet. And you can make 1 size n for the one. Yeah, I opened the problems. I didn't actually read them though. You can make 1 size 1. You can make 1 size 1 from the n, and then you can every other pair will give you 1 of size 1. All right. A competitive eater. Alice is scheduling some practices for an eating contest on a magical calendar, which does not have 7-day weeks. She can choose any integer k from 1 to r and set k days a week aside. Or instead, k days a week, so a week has k days. She's going to paint some n consecutive days in this calendar. On this calendar, dates are written just like a normal calendar. Considering the shape of painted cells, 2 shapes are the same if you can make them overlap using only parallel moves parallel to the calendar's sides. So are these all different? These look different, I'd say. 1 and 2 are different shapes, but 1 and 3 are the same shape. Okay, how many possible shapes exist if she set how many days a week she has chosen for n consecutive days and paints them in a calendar started the following days of the week? Oh, wait. This might be an issue. Oh, you can't. They have to be consecutive block. Where they're all connected by side. So it has to be at least k. And everything is different, right? So the answer is at least, well, like n has to be at least k, and then it also has to be at most k. So what is this first? N. Wait, what is r? Oh, you can choose different k's. I see. And you set r days. What is r? Oh, r is the maximum k. Okay, so you can pick any k up to r, and then you pick n consecutive days. So if r is larger than, this looks like it's gonna just be some math here. If r is greater than n, greater than or equal to n, then r equals n minus 1. And then beyond that, what are we going to be doing here? So the two things that matter are your start mod k, or yeah, start modulo k. That matters. And then in addition to where you start, the width matters. And I think that's it, right? Because if you have any start that's like uniquely determined, given some picture, you can figure out where they start. And then the width is, yeah, the width is also important because that's just going to be the width of your picture. Oh, although, yeah, you can also do this, I guess. Yeah, okay. So this isn't true for r greater than n. So for n all the way up to, for n to r, the answer is just 1. Right? Because you can just have that 1 there. If r is greater than or equal to n, you can just have one parallel line. And then you care about all the small things. There's a song about that. So for, yeah, so that would be 1, and then the next for 2, there are 2 ways of doing it, right? There are these 2 for 2. Then for 3, there are 3. So it's just 1 plus 2 plus 3. So I think this is just like n choose 2, maybe plus 1. You only go up to r, yeah. Okay. I made the font size bigger for Div 2 contests where they don't matter for me. For real contests, it'll be what I like, but yes. So we read n and then r. Okay. So if r is greater than or equal to n, then return, parse this out, n choose 2 for n minus 1. And then in addition to that, we have the one way of doing it as well. Otherwise, this out and choose 2 for r. I think that's it. 4, 3, 1, 28, big number. All right, solid, easy problem. I like it. Anya is a girl so brave that she is loved by everyone in the city, and citizens love her cookies. She's planning to hold a party with cookies. Now she has A vanilla and B chocolate. She invited N guests of type 1 and B guests of type 2. They're going to come in some order. After coming to the party, they will choose the type of cookie to eat. There is a difference in how they choose that type. Okay. It's the first type. If V is greater than C, they'll choose vanilla. Otherwise, it's of the second type, then they'll choose chocolate first. So the only difference is if they're equal, right? If there's at least one cookie of the selected type, he eats one. So these ones are always helpful, I think, right? Those always eat whatever there are more of, or chocolate. These ones eat whatever there are less of, or chocolate, or vanilla if they're the same. Okay, so we want to see if we can eat lots of cookies. Oh man, lots of cases here. Lots of cases. This is the classic I'm gonna forget a case problem. So what are the cases? We have, if there aren't enough cookies at all, then we're in trouble. What if we just let these ones go first? So then if you have like some vanilla and some chocolate, so maybe it's like 5 and 5, 5 vanilla, 5 chocolate, then they'll eat a vanilla, so then it'll be 4, 5. Oh, then they eat vanilla again, 3, 5, 2, 5. 1, 5, and then we're in trouble. Okay. So, yeah, these guys are always going to be a problem. The second type is always a problem. It seems like they should always go first. It seems like you should just unleash these people first, and then they'll have eaten a big chunk of your cookies, but then these ones will always be safe because they eat whatever there's more of. So let the greedy guys go first. Yeah, I don't think equality is important. Don't take that out of context. I don't think considering the case in which V and C are equal is important. Oh man. Yeah, because you could just swap them, and then any argument you could make for one order, I think, would be the same for the other order. Because they'll just eat the different type. So my hypothesis is let these ones go initially, and if they're safe, then this will be fine. So second type eats 2, and then we're fine. Okay, second type eats 1, not fine. Second type eats 1, but then you run out of cookies. Second type eats 25, and then you're fine. Second type beats none, but you run out of cookies. Second type and first type, yeah. Okay, that's fine. These need to be longs. Alright, so if A is less than B, else then A minus equals T2 if, well, or really all we care about is the min. So if math.min A and B is less than or equal to T2, less than really, then sys out no. Otherwise, that means T2 will be fine. So if A plus B is less than T1 plus T2, then we'll run out of cookies. The answer is just no. Otherwise, I think we should be able to do it. By these people go first, then these people clean up the rest. Yeah, I don't think that's going to be an issue. Like, I feel like that should probably be fine. I guess we'll see. Grid 0, okay, 0, 0, 1, 0, 0. Dr. Jabal has made a competitive programming task. Let's solve it. You have integers n and k in a grid A that's n by n, consisting of integers 0 and 1. A very important condition should be satisfied. The sum of all elements is exactly k. In other words, the number of 1s is equal to k. So we have a bunch of zeros. We make k of them 1. Exactly k? Yeah. So this is, yeah, okay. R equals, is it row column? Usually it's row column. Row I, so like the sum of this row and the sum of this column. So this is the sum of the ith row, sum of the jth column. Row sum, yeah, okay, yep. For grid A, let's define the value f of A equals the max minus the min row sum plus the max minus the min column sum. Here for an integer sequence x, we define max, the maximum value in x, and min is the minimum value in x. Yeah. Find any grid which satisfies the following condition. What are we doing with f? Oh, we want f to be minimum possible. So we need to put k1s in this grid that minimize the difference between the max and the min. Can we do it like along the diagonal? Well, is that just the case? Can we just put it along the diagonal? I have no idea. I feel like we should be able to. Is there ever a better way of doing it? It would be super nice if there were a better way, if it would put in samples. Yeah, I don't. Well, we're gonna need print writer for this anyway, so that's fine. Okay, int. Oh, it's always square. Does that matter? I don't know. It feels like that feels pretty easy. Because you'll have one in each, and then you'll have a couple offset. Can you do better? I don't think you can do better. You definitely can't do better. Yeah. I don't see why bounds are so small though. Maybe for multiple test cases. Oh, so now. K is less than n squared. Okay, so for int I equals 0, plus k is greater than 0, then k minus minus board at start plus I. This needs to be under mod equals 0 or equals true. There you go. Oh, and this needs to be print writer. This needs to be print, not print line. Same here. All right, 2, 2, we print this thing. 3, 8, we print that thing. 1, 0, we print the 0. I thought there were 3 zeros here. Wait, what are we printing? Oh, the minimum possible value. Oh, that's Nonsense. That's ridiculous. Why? Who cares? Who cares? Ugh. Okay, fine. Min are, well, it's always going to be 0 or 1, right? Or 0 or 2. Wait, what are we printing? 3 lines for this. Oh no, this is just 0. Yeah, so it's always 0 or 2. Okay. So if k mod n is equal to 0, then we can do full stripes and sys out 0. Else sys out print 2. Okay. I guess that wasn't that bad. So 0, this thing, 0, this thing, 0, this, 0, this. Wait, this should be 2 though. K mod n. 8 mod 3 is definitely not 0. Hello, what's up? Yeah. That's the original K mod n. Yep, cool. All right. Now on to the real problems.
Well done, sir. AC on problem D.
Yeah, okay. Cool. So E1, how much harder is E2? Looks like a decent amount harder. And then F looks like it's the real stumper. Okay, so let's read E1 and E2 for some fun. This is the easy version of the problem. The only difference between the versions is the constraint on N and AI. You can make hacks only if both versions are solved as usual. First, this person came up with the following idea for a problem. This sounds like a real story. Okay, this is a girl who collecting candies. I'm collecting candies too. I don't even know how to phrase this in first person. Originally, she has this many candies. She also has N, numbered 1 to N. This enemy has this many candies. This person is going to determine a permutation P. I didn't understand the sentence. What? Okay, so we have a bunch of enemies. Like, we have an array, basically. And initially, she has X candies. All right, she's got a permutation. We know what a permutation is. Thank you very much. After that, she will do N duels with the enemies with the following rules. That rhymed. If she has equal or more candies than this enemy, she wins the duel and gets a candy. Otherwise, she loses the duel and gets nothing. The candy which she gets will be used in the next duels. She wants to win all duels. How many valid permutations exist? The problem was easy and wasn't interesting. Well, it's not too easy yet. Let's define this as the number of valid permutations for the integer x. You were also given n, a, and a prime number p less than or equal to n. Whoa, okay. Slow down. This is the number of valid permutations for the integer x. For the starting integer. Yes, okay. So for some starting integer, this is how many permutations exist. So that if you shuffle them in this way, you will get something where you can beat everybody. Okay. You're given this and a prime number p. Let's call the positive integer x good if the value this is not divisible by p. Find all good integers x. If the value of f of x is not divisible by p. So find all starting positions, all starting values where the number of permutations is not divisible by p. The bounds for the hard version 10 to the 5th. Yeah. Oh, these go up 10 to the 9. Alright, well here's the real question. Do we solve both of these, or do we try and solve F? I guess solving both of them is just objectively a lot easier, according to the scoreboard. Like, it's 174 to 10 easier. And also, if we try and solve both and we don't get them, that's fine. Yeah. Though, well, there's not really much data to say which one's faster. They both take about 20 minutes. Yeah, I guess the good part about this is that if we get E1 but don't get E2, we still get partial points. So it's not like a total waste of time. Alright, so the first part of this problem seems to be this problem that's easy and boring. How do we actually do it? It wasn't interesting. How do we do it? My initial idea is maybe we can do something to take advantage of the fact that if we're gonna win every duel, then we just have one more candy in the next duel. So, are there any good samples for me to use? This is surely impossible, right? Oh, I guess it's not impossible. Well, like for a given permutation, the bound for it, let's say we've got some numbers like 2, 4, 3, 7. So the first one we subtract 0, second one we subtract 1, third one we subtract 2, fourth one we subtract 3. And that's how many we needed to start with in order to win. So if we do that, then we're left with 2, 3, 1, and 4. And we just care about the maximum. The maximum there. So if it's impossible, then there are 0 ways to do it. Well, yeah, okay, so we pick the number we start with. Then the question is how many, like we pick the number we start with, we want the number of permutations for that starting point to be not divisible by a prime. So yeah, what's the formula here? Like, how does this wind up working? So if we have 2, 3, 4, 7, let's say we start with 3. Then in the first position, we can have, well, we've got a bunch of groups, right? So then it'd be like 3. If we start with a 3, the first position is going to be, will be 3, then 4, then 5, then 6. Those will be our power levels. So if we have like 2, 2, 3, 5, that's an interesting example, I think. Maybe 2, 2, 5, 5 is more interesting. So this can be in 4 positions. This can also be in 4 positions. Seems like it's probably more useful to go from the back, at least. Like if we go from the end, then we know, if we know the starting value, Then if we go from the end, yeah, so it seems like the solution path for E1 is going to be, like, what was the time difference on geothermal submits? It's nice being an hour after everyone because you can see how long it took everyone. So this was an hour initially, but the first submit took like over half an hour. So yeah, so you definitely did E1 first and then moved on. For E1, yeah, okay, I should definitely be able to get E1. For E1, it seems like it's going to be brute force this AI because the answer is going to be one of these AI things. And P is smaller than N. Yeah, it seems like it's going to be brute force this AI thing and then just count it and then just check. So like the naive should be pretty easy to do at the very least. So the 5, if it's 3, 4, 5, 6, there are 2 positions for the 5. So this is like you have to distribute these things in 2 ways. And then for the next biggest thing, we have to distribute them in 4 ways. So we have 2 open spots. So this is like, we have 2 things and 2 positions we can put them in. And order matters. So it's 2 factorial over 0 factorial. This again, we have 2 things and we have zero places we can put them in. So 2 factorial over 0 factorial. Well, since we're short on time, I feel like maybe just writing up this solution might not be a bad idea. Man, I cannot type. fs.next. Okay, so we've got this integer. We also have the max prime. Or we just have the prime here. Entity. So now the question is, we need the array too. So now, well, it doesn't hurt to sort it, right? Probably not, because we're looking at permutations anyway. So now the question is, how many permutations are valid for this? So we should probably brute force our starting point. How many integers x are there that aren't valid? Oh, weird. Oh, it's only one test case. Okay, good. For E2, it's guaranteed. Is this guaranteed for E2 as well? Surely it's only 2,000. It's only 2,000, right? this is less than n, and it's very big, then yeah, this is definitely a false herring, or a red herring. False constraint, I don't know what to call it. We'll have some x, which will be the starting value, and then some array, and then some prime. So if try x for the start, the array, and the prime, then add this x, and then print it out at the end. So now we're just left with this method here. So how do we do this? We can make the caps, but it might be easier to just not do that. Yeah, I think it's easier not to. In that case, what we can do is we can go from biggest to smallest. Does it matter? It matters how many of these there are. Yeah, that's important. So, like, some element of A can only be in a spot that is less than or equal to, or in a spot that's greater than or equal to it. So I guess let's just make this. Right, now int, well, all these are unique, so this is easy. So now we can just do this. So we can do 4 int, and we need like a int next a equals n minus 1. How do we do this? So the spot to fill is going to be equal to n minus 1. So while, yeah. So while the next thing is bigger than the spot, that means we can't place it here, which means we would have to place it before here. Okay, so we'll keep track of how many spots there are. We also need to keep track of how many we need to place. And now what we can do here is we can increment how many we need to place, because we need to place this one now. So we'll increment that, and then what else do we need to do? We need to decrement next day. Yeah, so now we have all of these things we need to place. Yeah, blah, blah, blah. Okay, and now spots earlier minus equals all of the things we need to place. Because we need to place them in those spots, we'll lose the spots. And then after we do that, we get this new spot. So if it's ever less than 0, that means it's impossible, so there are 0 ways, which means 0 is divisible by p. So this one will work. If it's never impossible, then we might have an issue. So, or we might be okay. So then otherwise, like the number of ways times equals what do we multiply by? We multiply by the number of ways of placing this many things in this many spots. So that's going to be so the value is going to be spots earlier. There are that many ways to place the first thing times spots earlier minus 1, that many ways to place the second thing, etc., all the way down to, well, I guess it's this, yeah, minus, okay, so we place, but how many of these are there? There are minus, need to place. So if p is less than or equal to spots earlier, and p is greater than spots earlier minus need to place, then we'll multiply a factor of p into our answer. So the answer is going to be false. If we never multiply a factor of p in, this is just going to be the product of a bunch of numbers, in which case we can return true. No, not quite. We got 2 right, I guess. Well, for one of these big numbers like 10, what is it going to be? It's going to be 4 factorial. Or it should be 4 factorial at least. There should be 4 spots. And we can place 4 things in them. Or I guess, what is this? This is start. Probably a stupid mistake here. I need to place 0, need to place 0, need to place 0, need to place 0. I see. Yeah. So we need to do this whole thing one more time. We need to do this for we need to do it here because now we're out of room. What is the solution to that? Alternatively, can we just modify our array slightly? If we, well, not really. We can't. Greater than or equal to -1 maybe. So if we're at the like last spot, if we've used up all the spots, then it doesn't matter what our value is, we need to place it. So I think that's fine. This is not, I don't think this is a good way of solving this problem because I'm going to need to do the math as soon as I want to solve the hard version of the problem. Do I need a print writer? I think I'm only printing 2,000 things, if my understanding is correct.
Well done, sir. AC on problem
Okay.
1.
Well, that's unfortunate at best because because I'm in trouble. So yeah. Well, like, what do? I don't have any math done. I don't have any, like, I just did a bogus solution to this E1. That was pretty much just trash. Like, this isn't, I guess I'll read F. How about that? You're a warrior fighting against the machine god Thor. Thor challenges you to solve this problem. All right, cool. There are n conveyors arranged in a line with integers from 1 to n left to right. Each conveyor is either left or right. Initially, the state of this conveyor is equal to the ith character of the string. There are a bunch of holes, n plus 1 even, 0 to n. This is the left side of conveyor 1, otherwise they are between the conveyors. When a ball is on conveyor this, the ball moves by the following rules. If it's left, then it either falls in hole 0, otherwise it moves to the left conveyor, wait. If I equals 1, the ball falls into hole 0. If the symbol is left, if the symbol left is on the conveyor on -1, then it falls to the left. Oh, so like if they're going the same way, it continues falling, or it continues going until it hits 1 going the other way, then it falls in the hole. You should answer the next Q queries. Each query is defined by a pair of integers, LR. First, for all conveyors, L blah blah blah. Change the symbol this to this or vice versa. These changes remain for the next queries. So you have range flip. After that, put 1 ball on each conveyor here to here. Then each ball falls into some hole. Find the maximum number of balls in 1 hole. After the query, all balls disappear and aren't considered for future queries. Wait, is this just the same thing as Sneetches? Oh man, dude, I wish I would have done really well if I did this round. I think this is the exact same problem as Sneetches. Darn. Man, I should have read this problem before doing E, because I definitely could have gotten this one. Yeah, so this is range flip, and this other one is range query the maximum thing in a range. Right? Query the maximum number of... So if you just do sneeches on a tree, but then you're set. Do I have time? 9 minutes? I don't think I have time, but... Yeah, so, well, I can go over the solution to this problem. Oh, wait, that's not true. Because... Yeah, it's not entirely true because, like, the balls in a hole are, like, they can come from two different directions. So it's not just a continuous range. It is kind of a continuous range, though. It's like, in a sense. Yeah, this is an interesting problem. It's a good problem. I like it. I wish I didn't miss an hour of the round. Because this seems quite doable. So, I mean, what do you need? Maybe I'll draw here, because I'm kind of out of space. You need, you've got, like, some segment. If you've got your two kids, you need to know a couple things. You need to know the max, like, thing within your range. To do this, you're going to need to know the max within your two kids, or it's possible that it crosses the kids. So you're going to need to know the, like, this thing suffix, this thing plus this thing suffix. Then you're going to need to know this thing prefix, or no, you only care about this prefix. And then you also care about this thing plus this thing prefix. All right, these are all very easy to maintain. What else are we going to need? Well, we're going to need lazy prop. And we can maintain, oh, we can't maintain this. So in order to maintain this, we're also going to need the max this within range. And what else are we going to need? We're going to need the to maintain this suffix, we're also going to need to maintain this suffix. We're also going to need to maintain this plus this would be the equivalent of this plus this. And this prefix, so we're going to need the opposite of that prefix. So there's like a lot of maintenance here. We would need this prefix. And then we would also need this prefix. So like, oh man, darn dude. Well, that's unfortunate. Yeah, and then you can maintain all of these things. So it's an easy segment tree problem, just with a lot of work to do, which I won't be able to do in 5 minutes. All right, let's maybe let's think about E2 for the next 5 minutes, and we'll we'll play this as like a thinking round instead of a coding round. So what is my math currently doing for this? To try a given x coordinate, I multiply by a continuous range Well, okay, one thing that I could abuse that I'm not is that this array, or this spots array, is almost always the same. Yeah, it's almost always the same, so you can take advantage of that in the following way. Like, the only thing that matters are groups of the same number, and because groups of the same number will all be affected in the same way, and then the prefix and the suffix also matter. You want to know if any of those groups are a certain size. All we care about is if this spots earlier, we only care about how big it gets. So if we remove this condition, I'm pretty sure that doesn't change the solution, because this condition is just the lower bound of the factorial, but this lower bound is going to exist eventually no matter what. So we don't care about this lower bound of the factorial, we only care about this, or wait, if p, yeah. So let's, I guess, make this easier. If spots earlier is greater than or equal to p, that means that it's going to be divisible by p. Yeah, there we go. Because like this will be like, it'll be like 6 times 5 times 4, right? And then that will change our number of spots from 6 down to 3. But then later on, eventually we're going to multiply 3 by 2 by 1. So it doesn't actually matter that we're not doing it now. Like, it's true that we're not doing it now, but that doesn't matter because eventually we'll do it. If the number of spots ever gets to 6, then we'll do it eventually. So the number of spots, all it is going to be the prefix, then individuals in the middle, and the suffix. But it's not quite just individuals, because like the spaces matter, I think. Because there are some zeros, and when there are... Or no, that's not true. Yeah, I mean, it changes in a predictable way. So that's, I guess that's what you have to do. You have to figure out, kind of on paper, how to predict this. Because like it's yeah, it's not random. It's very predictable. You can, if you work on it for a while, you can figure it out, I think. Yeah, well, okay. I guess let's go over solutions, because that's the end of the set. So, easiest to hardest, as usual. Problem A, magical sticks. Yeah. So you have n sticks, 1 stick of each length. Yeah. So you've got like 1, then you have, well, I guess let's just draw out the numbers. So this is 6 is a good example, I think. So what we can do is we can pick sticks of length 6, and we can have this 1 stick of length 6, then we can have all other pairs of numbers like that. So now 1 plus 5 is 6, 2 plus 4 is 6. So we have 6 plus 1 over 3. That's how many sticks there are here. That's always going to be the case because since you only have one stick of each height, you can't ever do better than this. Like you can have one stick that matches perfectly. In the rest of cases, it's going to take at least two. So we can get our first stick here. The rest of them will take at least two. And we can do it here. We can't ever do better with anything else. So this is just, that's the answer. The reason it's like plus 1 over 2 is because this is going to be, it's like 1 plus 5 over 2 floored. That's an equivalent way of writing it. Because we get this 6 for free. Then these, every pair of them make 1 point. All right, let's look at problem B. Problem B was, I guess you had to be a little careful. It's pretty easy, I thought, but I guess bounds were big, so maybe a little bit scary. Okay, yeah, so in this problem, you've got some calendar, and your calendar has like some bounding box, like this. And what you're gonna do is you're gonna write a continuous block of n days, like this, and you wanna know how many different shapes you can make. So the first observation is if it's like bigger than or equal to like the length of your block, so if it's just gonna be like this, then you can have them all in a row, but the only other thing you could do if it's like this size is you could do like some suffix and then some prefix, but these won't reach each other. So if like n is bigger than or equal to r, I think is r is the max days in a week. So if if r is bigger than or equal to n, then for this part you just have the one way. So then this is like plus 1 for r's, like for just like a straight line. All right, so then what else is there? We also have for everything smaller than n. So if r is going to be small, that means you're allowed to overlap, so that's fine. So it'll look like something like this maybe. And you're guaranteed that it's like one continuous block because you can pass this point because you're bigger than n. So since you know it's one continuous block, there are two things that can determine what this shape looks like. The first is going to be the width of this shape, and the second is going to be this like how many open spaces you have in the beginning here. So let's like look at how big the width can be. So if the width is 1, that means you're just going to have like a bunch of things like this. So there's only one way of doing it. So if the width is 1, it's just 1. If the width is 2, there are two possible starting points. You can either start here or you can start here. So then it's like 2 for that, then it's 3 for the next thing, 4 for the next thing, 5 for the next thing. This is a very predictable pattern. We can notice that if you add these pairs up, then what you'll get is you'll get like these are 2 times 3, these are 2 times 3. So basically we can convert everything into 3s. Or alternatively, it's just n choose 2. So the formula for this is going to be like n times n plus 1 over 2. And we can do this to count all numbers for all r's less than n. Okay, system tests are gone. Problem C. Okay.
Well done, sir. AC on problem 2. Well done, sir. AC on problem A.
Huh.
Problem 2 got time limit exceeded test answer.
Give me a minute. Yeah, so system tests go on, so my submissions, like could force messing with submissions, which causes that to bug out. Yeah, all right, so that's problem B. Problem C. Oh yeah, this was, I thought it was a good problem. It was very easy, it was a good problem. So the idea is that you have two types of people. You have types of people that will eat whichever cookie you have more of, and types of people that will eat whichever cookie you have less of. And you know that the people who will eat whatever you have more of are safe to put last because they'll just eat up like the crumbs that are left over basically. And then the people that are very demanding, you have to put first because they're just gonna like eat you where you have the least amount to spare, right? So they're gonna like stab you where it hurts, I guess. So you want to make sure that you get stabbed while you have as much free cookies available as possible. And then once all those free cookies get taken away, you'll give them to the people who will just eat the crumbs that are left. If you think really hard about this, it's a lot about life. And it's like a very moralistic view of life. I don't know if it's right or not, but it is what it is. So you want to see like if the chocolate people can eat, or if these evil people can eat all of your smaller amount, then you're going to be in trouble. So you won't be able to satisfy everyone. So you can just say like if the bad people, I think that's type 2, is greater than or equal to, or is greater than, rather, is greater than the min of vanilla and chocolate, then it's impossible. Otherwise, if you don't have enough cookies to feed everyone, then it's also impossible. Otherwise, it is possible. So yeah, that's the solution. And if you needed to extract it, the way of doing it would just be feed all of these type 2 people, and then feed all of the type 1 people. And it's pretty clear you can't do better than that. This is another thing where it's also pretty clear you can't do better than that. So if you have a square grid, you can, if you've ever thought about, I think it's called Latin squares, I think is the official name of it. It's a square where each row and each column only has different numbers. So like there are no duplicates in a row, there are also no duplicates in a column. And I think sometimes there are magic Latin squares, which have the additional constraint of all rows and columns summed to the same value. But if you have a Latin square, one way of constructing a Latin square is you can just put 1s down the diagonal, and then you can put 2s down the next diagonal, but like the next diagonal would be here, so you just like shift that around cyclically, so you make it here. Then you put 3s down the next one, and then you put 4s down the next one. And clearly in each column, like this is the same thing but shifted over. So since it's shifted over once for each one of these, then we'll have 4 different numbers, and same thing for each row, because each diagonal only hits each row once. So if we do things in this order, if like k mod r or k mod n is equal to 0, then we know we'll do the same number of diagonals for each row and for each column. So then we'll like have the answer of 0. If k mod n isn't equal to 0, then I'm pretty sure at least there's no way of doing it. Because if we do it, like, then we have to do this diagonal thing. There's not really a better way of looking at it. So we're going to have some big rows and some small rows. That means the answer is going to be equal to 2. The proof for why that's true is because you know that they can't all be the same, right? So if we look at this formula, we know not all rows can have the same number of elements, because if they did, then there are n rows. So if they all had the same number, if you multiply that number by n, that'll have to be equal to k. But we know k mod n isn't 0, so that's not going to be the case. So you know this value, you know 2 rows have to have different values. So this has to be at least 1. This also has to be at least 1. So there's our proof. Okay. So yeah, otherwise what'll happen is you'll fill in something like this. So you'll fill in like these, and then you'll fill in a couple of these, maybe. So now you'll have this row here has 2, and this row here has 1. And since you were between filling in 2 and filling in 1, you're close enough that the answer is it's going to be 1. 1 for the rows. Same thing for the columns, or same thing for the rows for the same reason. Yeah, so that was a doable problem, I think. Probably good to upsolve. E I can talk about, and then I'll explain how I would go about approaching E2, but I didn't have much time to do it, so I can't give hard details on that. But the idea for problem E is you've got some numbers, I guess. So like the initial problem is you have some numbers, maybe it's like 5, 4, 7 to 12. And then you're gonna, like, these are the monsters you're gonna face, and if you beat a monster, you get +1, and you want to beat all the monsters. So if you beat this, then you'll have +1 to go fight this one, you'll have +2 to go fight this one, because you'll have 2 points from each of these, +3 for this, and +4 for this. And what we can do is we can keep track of what do each of these spots say your starting power has to be. So for the first position, you need a starting power of 5. Well, I guess let's keep track of this. Well, let's do it slightly differently. Let's say we know what our starting power is. So maybe our starting power is going to be like 10 is a good example. Maybe 10's a bad example. Yeah, 10's a fun example. So that means on the first battle, you'll have 10 health, then you'll have 11, then 12, then 13, then 14. And now we have these 5 numbers. We want to see where we can put them. So this 12 we can put in any of these 3 positions. Any of the other 4 numbers we can put in any of the positions. So if we go from the right to the left, what we can see is when we hit this 12 right here, in one of these positions we're going to have to put, yeah, I guess when we hit the 11 really. When we hit the 11 we're like, okay, in one of these 3 positions we're going to have to put this 12. And the number of ways of doing that are, since there's only one number, there are 3 ways we can place it. If we had like a 12, and let's say that we had this as like 12 as well, we had 2 12s maybe, then what that tells us is in these 2, or rather in this position here, we need to place 2 12s. There are going to be 3 ways to place the first one, and then there are 2 ways to place the second one. So maybe we place one here and we place one here. In the future, it doesn't matter where we place the 12s, because anything other than 12, anything smaller than 12, can be placed in this spot. And it could also be placed in this spot if we place the 12 and the 13 and 14. So all we need to care about is like how many spots we have after us, and we can handle that pretty well. And then when we get here, we're like, okay, we now have these 3 things left over. We have to place them in these 2 spots, plus we have one other spot here. So we have 3 things, we have to place them in 3 spots. The number of ways of doing that is 3 times 2. 3 ways for the first thing, times 2 for the second, times 1 for the third. So 3 factorial. And yeah, that's the total number of ways of doing it. So in total, what the formula would look like for this total thing is it would be 3 times 2 times 3 times 2 times 1. And we want to see if there are any factors of p. So what we can do is we can brute force this starting value here. And if we brute force the starting value, we can just check what would this be. And we can do that in order n. So then that will give us a solution to E2 in n squared. And yeah, that's it. So pretty easy. Or to E1, yeah. To E2 is harder. So I didn't actually solve E2, but one thing to notice is that most of these things change in a very predictable way. So you've got like some numbers that are bigger than this number here. And for all of these big numbers, that'll make it impossible. So if there are any numbers out here, then it's going to be impossible. And really, you can think of it like a bracket sequence, kind of. So if you think of it as like a bracket sequence, then every time you have like a 12 here, like we have this, so we're going to go from beginning to front. So this 14 is like an open, 13 is also an open, and then this 12 is kind of an open. But now we have these 2 12s, which correspond to like 2 closing brackets. And when we do this, then what the counter will be and how many open brackets we have. So let's complete this one actually. So we have we've got 12 12, and then we have these 2 more open brackets for the spot 11 and spot 10. Then we have 3 closing brackets for 7, 4, and 5. So when we do this, if we keep track of the counter as we go, it starts at 0, and then here it's going to be 1, 2, 3, 2, 1, 2, 3, 2, 1, 0. And you can notice the biggest number here is going to be a 3. So we can these two 12s, we can compress them from being two close brackets to like one bracket of length 2. So really it's like a 1 but like a times 2 sort of thing. And I think that might be easier to code. And then we have all of these things, but these are all at the end. So although they're all separate, the 7, 4, and the 5, they're all at the end, so they're also predictable. And basically what we need to do is we need to take all of these things and move it over by 1, and then see how does this change the maximum value in this counter. And I don't know if I explained it thoroughly, but the maximum value that this counter gets to is going to be equal to the biggest prime that shows up. So all you care about is this maximum value bigger or smaller than p? And if it is, then you can handle things accordingly. Alright, so that's that problem. I don't have like super solid implementation details because again I didn't actually code it. F. Good problem, I think. So you have a bunch of less than or greater than, and you have like imaginary holes in each position here. And now if you drop a ball here, it will roll in the direction of the arrows until it hits an arrow of the opposite position, and then it'll fall down in the hole between them. Yeah. Okay, so that's the problem. Oh, I guess the problem is you also have updates and queries. So the updates are like flip a certain range, so flip this range. And then the queries are in a given range, like in this range, for instance. Figure out what if you dropped a marble in each position in this entire range, then which hole would have the most marbles at the end? So like what's the biggest consecutive substring that looks like this, where it's like a bunch of greater thans followed by a bunch of less thans. What's the longest substring in some range that looks like this? So you can do this with a segment tree, or you can do the first part with a segment tree at least. I think if I implemented this, I would probably use a tree because you can easily split and then like range flip. And then you can do your queries pretty easily, I think. But I don't know, maybe segment tree is easier. Yeah, it might be easier. I'm not really sure. The idea is this. So you've got some ranges. I talk about this a lot in my segment tree video. In the Sneetches problem, it's very similar in nature. But the idea is that you've got some ranges in your two kids, and now you want to find the biggest range in yourself. So in order to do that, there are a couple different cases. The likely case is the answer is going to be one of your kids' answers. So we need to store what the two kids' answers are, and then our best answer might be one of the two kids' best answers. It's also possible that it crosses the two kids. So if that happens, then we need to be able to calculate what the maximum crossing is, because it might not be a good answer for each kid. It might just be like something like this. So clearly this one is shorter than this. And then same thing over here, but when you combine them, it might be the new best. So we need to keep track of a bunch of stuff. Oh, hello. We need to keep track of like the maximum thing that looks like this. We also need to keep track of, in order to do this, like we need to keep track of the maximum one in our two kids. But it's also possible that it will be like some suffix here followed by some prefix. So we also need to keep track of like the max suffix that looks like this. And then we also need the max thing that looks like this prefix. We also might have a suffix that looks like this. And then this might be the border between the two kids, and now we might have just something that looks like this. So we also need the max prefix or max suffix that looks like this. And then we also need the max prefix. I guess I'll just follow the same format that looks like this as well. So we need to keep track of all of these things, and if we can keep track of all of these things, then we can build this answer for our parent. Okay, now in addition, we also need to be able to range flip. So we also need this like lazy prop value. And that itself is pretty easy to keep track of. The difficult part is when we add this lazy propagation value, then we might be looking at children who are propagated and who are inverted. So if we invert our kids, then we now need to know what is this value for our kids who are inverted. Which means in addition to this value, we also need to keep track of another 5 values, which are these 5 values but backwards. So like we need to keep track of the max one that looks like this in case it gets inverted, because if it's inverted, then we care about this instead of about this. Then we also need to keep track of the max one of this suffix, then the max backwards prefix, and then same thing for the other two, for these two as well. Because like it might be inverted, so we might need to look at that instead. Yeah. So then to answer range queries, if you do this on a treep, you can just split the treep in 2 positions and then look at the thing for this once it's recalculated. If you do it on a segment tree, what would you do? I guess it wouldn't be that bad to do a segment tree for it. So I guess you could just do this with the segment tree. You can do log squared really easily. I think you can probably make it just log. But the log squared is going to be low overhead. Like the first log will have a lot of overhead, but the second log should be really quick because there won't be any propagation or recalculation going on. So yeah. How big is n? Can we do log squared? 5 times 10 to the 5th, but only 10 to the 5th queries. And the queries would be the slow part. So I don't know. It's plausible. The n squared or log squared might pass. I'm not really sure. But yeah, that's the idea behind this problem. It's very similar to Sneetch's. So I guess I'll probably link that in the description. Hope you enjoyed the round. I hope you didn't miss as much of it as I did. But I'll probably, I'll probably upsolve F if I get a chance, because it's an interesting problem. Do I have anything judged yet? I have A judged. My A got judged really early, I don't know why. But it looks like system tests are quite safe. Yeah. So, that's all. Thanks for watching. See you in the next round, whenever that is. I know there's one on the 4th of July. Global round, so it'll be rated for me again. That'll be fun. Goodbye.